This video is about a method to solve the following trigonometric questions or simplify these trigonometric identities using complex numbers. Without complex numbers, you need some trigonometric identities in order to be able to simplify these numbers or find this cosine phi over 5. But trigonometric numbers and the relation between complex numbers makes these problems very, very easy. Or it's a different approach that avoids using trigonometric identities. So what's the relation between complex numbers and trigonometric identities, or just the trigonometric relation interpretation of complex numbers? Any given complex number can be written as follows, and this a plus ib, I is imaginary part, square root of -1. You can plot this in complex plane as follows, where a is real part, b is imaginary part, and then when you do the distance from origin to the point, it is the r, the modulus of the complex number. Using the trigonometric relation, if you say this angle is theta, then you can rewrite this complex number as in terms of cosine and sine and this radius or modulus. So to solve the problems with trigonometric equations, we will use complex numbers with modulus 1, where we have r is 1. And let's see the following three properties. So the first property is the following. Now let's try to find 1 over z. So if you say z is the following complex number, cosine plus I sine theta with r is equal to 1. 1 over z, you just do the reciprocal of that number. But you have to simplify this. You can simplify this by multiplying both numerator and denominator by conjugate of this number. So just like replace this. Here we have plus and this is minus. When you multiply these, you get a square minus b square formula basically. And then the denominator turns out to be 1, because this is cosine square and sine square. That gives us cosine theta minus sine theta. So in terms of cosine and sine, the only difference between z and 1 over z is this sign. If you do plus I sine theta, it's z. If you do minus sine t, it's 1 over z. So that's the first property. The second one, what happens if you add this z and 1 over z? Since we have plus and minus, so these imaginary parts cancel out. So z plus 1 over z is always a real number, which is equal to cosine theta, twice the cosine theta. So we have basically going backwards, we have a formula for cosine theta. So cosine theta is half of z plus 1 over z. So all the three problems are related to cosine, so we are going to use this one. But if you have similar related problems with sine, you can use the formula for sine as well. And the last one, number 3, property of complex numbers relates to its powers. So when you have a complex number, this is a well-known formula. If you want to do the nth power, you don't have to multiply, open the parentheses, like do the square, multiply the number by itself. In cosine form, you just need to multiply the angle by n. So Zn is cosine n theta plus I sine n theta. So in other words, if you do square, just 2 theta here and 2 theta here. So, or if you want to do z to the power 5. So this kind of simplifies our work. So like if you want to do powers of z, it's straightforward, just multiplying the angles inside the arguments inside the cosine and sine. So let's move on to the first problem. So for the first problem, I'm going to use the following complex number with the angle pi over 7. because we have cosine pi over 7 here. And if you want to do 7th power of that number, so that's very important property, you just need to multiply the arguments by 7, right? But when you multiply by 7, you get cosine pi plus I sine pi. And this part is 0, this is -1. So this one turns out to be -1. So z to the power 7 is basically -1. This is a very useful information that we are going to make use of in the upcoming steps. So let's, the cosine pi over z, pi over 7, so that's 1 over 2 z plus 1 over z squared. So that's the first property that we have derived before. And what will be cosine 3 pi over 7? So, or cosine 5 pi over 7. So you could do like z cubed and then z to the power 5 and get similar formulas for these second and third terms. And then basically your entire expression becomes the following. It's kind of, z is a complex number, but this part, simplifying this expression, basically becomes an algebra. Instead of doing trigonometric identities, it just became like algebra. You want to simplify this. But these numbers, z has some properties related to this one. So that's something we want to use. So we'll do the common denominator. So the highest power is 5. So you do z to the power 5 and then the rest. And one thing to note is use to z to the power 7. And then you can reduce the powers that are higher than 7. You can use that the following. Z to the power 10 is z7 times z cubed. So 7 plus 3. And z7 is -1. So that gives me minus z cubed. So z to the power 10 is minus z cubed. And z to the power 8, you can rewrite it as follows. That's minus c. So we have an equivalent of these two terms with lower power. So the expression becomes as follows. So we replace these two with z cubed and then z squared, this and this negative terms. So this may not be familiar, or this like if you are not experienced, this may not give you say anything to you at this point, but there is one property that we are going to use a lot in the future. So this, the powers are 6, 4, 3, 2, 1, 0, right? 5 is missing. So let me add the 5 here and then remove the 5. So it's this z5 and z5, they are basically 0. And one thing to note in this line, so we have the signs alternating, plus, minus, plus, minus, plus, minus, plus. So this can be rewritten in different forms. So that's one of the main ideas of all three problems, basically, or one of the main ideas of this method, I would say. So z7 plus 1, it can be factorized as z plus 1 multiplied by this number. So we have that number here, like this expression, and we have that expression here, this one. So basically this part, except the last z5, you can rewrite it as z7 plus 1 over z plus 1 and plus z5 over. So this expression here can be simplified further. Z7 plus 1 is 0 because z7 is minus 1. So this term is 0. So we are left with z5 over 2 z5, and which is just 1 over 2. So this entire expression is equal to 1 over 2. So using the complex numbers, we have been able to transform the problem into an algebra problem, and use this property to simplify this expression. Now the second problem, the product of cosine 20, 40, and 80. So in the first one we had the sum, now it's product. We'll use the similar tricks. So let's start with z is cosine 20 plus I is 20. So the square of that number will be cosine 40 plus I sine 40, because we are taking square, so you need to multiply double the argument. So we will use this because we have cosine 40 here, cosine 20 here, so that's kind of related to our problem. And cosine 80, take the fourth power, right? So one more thing to note, so as in the previous problem, which power makes that number, which power of z makes it real number, or which power corresponds to pi. So if you do the z to the power 9, 20 times 9 is 120, 180, 180. So if you do the z to the power 9, you will get cosine 180, I sine 180. So this part is 0, this is -1. So z to the power 9 is -1. So this is one of the properties of z that we are going to utilize in solving the problem. So you can, so that's the, going back to the previous problem, that's the expression z9 plus 1 is 0, and you can factorize it as z plus 1, and the power z8 minus z7 plus z6 minus z5, and so on. Now go back to the problem. Let's find expressions for cosine 20, 40, 80. So it's the second property. So if you multiply these three expressions, we get the 1/2's make 1/8, and product of these three expressions. Using the first z8 is -1, we can get rid of these fractions. That's another trick. So you can 1/z is equal to minus z8, because if you multiply both sides by z, you get z9 is -1. So by just dividing z9 by power of z, you can get equivalent of these fractions. So if you replace them, you get an expression without fractions. Then you can open the parentheses, there will be 8 terms, then you can simplify those 8 terms, right? So the 8 terms, and the terms starting the third one, 12, 13, 14, 15, 19, 20, these are all greater than 9. So you can use z9 is equal to -1 to reduce the degree of these 6 terms, as we did in the previous problem. So reduce the powers, and now when we reduce, you can rearrange these terms, because we have, like, it's kind of related to this factorization. We have 8, 7, 6, 5, 4, 3, 2, 1. We only don't have 1, 0, z to the power 0, but we have all the other terms. So I can rewrite the expression as follows: 1 minus, and this term. I'm writing it as minus because z8 has a negative sign in front of it. So if I put parentheses here, that will be inside the parentheses, z will be positive. So I can use it here. And then this term is basically z9 plus 1 over z plus 1. So that gives me 0. And since this part is 0, the entire expression comes up to be 1/8. So this product of 3 cosines using these complex numbers is equivalent to 1/8. So there is another way. You can use the double angle formula for sines to simplify this expression. But you need to know double angle formula and need to know several properties of cosines and sine. You need to be able to manipulate with cosine and sine expressions. So this is kind of transforms the problem into an algebra problem, basically. And the last one is, let's find cosine pi over 5. So we are given that it's 1 plus root of 5 over 4, but so basically we want to find this expression, right? The value of cosine pi over 5. Since pi over 5 is, I would say, if you do, it's around 36 degrees. Yes, it's exactly 36 degrees. And then what you want to do is to find the exact value. So that's first quadrant, and that should be a number that's between 0 and 1. So when we do our calculations, if we end up with negative number or a number that's greater than 1, we are going to ignore those numbers because we are looking for a number that's between 0 and 1. So as usual, start with the following complex number, and cosine pi over 5 is the following expression. So this is the second property. Let's say cosine pi over 5 is x. That's something what we are trying to figure out. And then if you take the fifth power, that becomes, again, so this multiplies by 5, this multiplies by 5. z5 is negative 1. So let's factorize z5 plus 1 is equal to 0. So this is the factorization. Since the first part is not equal to 0, because z is not 0, negative 1, this part is not 0, we could be looking just only to the second parenthesis, because the product of two numbers is 0, so one of them has to be 0. So this is 0. So what we want is to solve this equation. But we know the solution of that equation, but z is this one. If I solve this equation, one of the solutions is going to be this number. But what I want is to find this x. So I need to transform this equation something that has x in it. So I'm going to divide the expression by z squared. So when I divide by z squared, every degree will decrease by 2. And then if I reorder the terms, I'll have the following equation. So z and minus 1 over z is here. So this one kind of relates to x. And then I can rewrite this as a square of z plus 1 over z. And then that will be also relates to x. So I can rewrite as z plus 1 over z squared minus 2. If I open the parentheses and subtract 2, I get z squared plus 1 over z squared. And then this term are same. Now you can see that z plus 1 over z is just 2x. So this one is 2x, because here x is 1 over 2, z plus 1 over z, multiply by 2, that's 2x. And this one is also 2x. So basically you have 2x squared minus 2 minus 2x plus 1. So that's the equation. If you simplify it, it's just a quadratic equation. So this quadratic equation has two roots, but one of the roots is our number, cosine pi over 5. The other one is something irrelevant, but one of the roots has to be our number, the number that we are looking for. So the criteria for our number is the number that we are looking, it has to be positive between 0 and 1. So that's one thing to keep in mind. Let's solve this quadratic equation. It's just straightforward quadratic formula. Do the discriminant and simplify everything. So discriminant is 20, and use the quadratic formula. And then the first, if you simplify, the first root is 1 minus root of 5 over 4. That's a negative number. So that's the first root is not that number that we are looking for. And then if you look at the second number, that's obviously 1 plus root of 5 over 4. That's the number we are looking for. So one of the roots has to be our number. So this is the number that we are looking for. This is our number. So x is equal to 1 plus root of 5 over 4. And we defined x as cosine pi over 5. So basically cosine pi over 5 is equal to 1 plus root of 5 over 4. So this is these three problems is basically illustrates a way to transform a trigonometry problem into an algebra problem, where you can do your operations more easily, or that could be more convenient for some of the people, for somebody who is more familiar with the algebraic tricks. So that's one option to solve this type of problems.